Okay, so in the previous session, we are discussing related to different structural system. So initially, we took the rigid frame system where the rigid name, so it is the joint between the two structural elements. Okay, so here frame is nothing but combination of multiple numbers. Okay, it is combination of both column and frame forms a column as well as beam forms a frame, right? So here in rigid connection, where you can see the restrict in the translational movement and as well as the rotation. So where in case of pin joint, so that you can particularly you can see that type of pin joint in the trusses, where the trusses are designed for only the forces, where you will find the member forces, whether it is the tension or compression, what will be the magnitude, right? So where the moment will be zero, okay? Because in pin joint it can rotate in any 360 angle, right? So for that moment will be zero. And we are looking into how the rigid connections are to be considered both in the steel structure as well as for RC structure. And these are all the few connections that I have shown. And in order to design the rigid frame, so what are the considerations that we need to consider? Okay, so that also we have discussed. So here design consideration or drift. In the first is the deformation to the cantilever bending of the building. So it is of 20% of the total lateral drift. So what is drift? So let me check what exactly is the drift. So there are few technical terms, translational drift. So that has to be discussed in detail while discussing in lab. So that is the deformation between two stories. Okay, the difference in deformation between two stories are called as drift. Somewhere over here. Story drift. Yeah, story drift. So as I mentioned, the relative displacement between the floors and above or below the story under consideration. Okay, say for example, so here we cannot discuss. Yeah, so let me go over here. Say for example, if I just draw the datum line, so you can see that the displacement of this floor. Okay, so the displacement of again this particular floor. So you need to consider the displacement of both above and below. So if you do the average with respect to the floor of height of the floor, so you'll get the drift. Okay, so that I'll discuss while doing the lab. So what exactly is drift, translational, how to get the torsional as well as translational movement, how to find the translational movement, and that and all can be considered and can be calculated by using software. Okay, so here in this case you can expect around 20% of total lateral drift. So 20% of total lateral drift. So where in the second part, so the same thing, it is a deformation due to bending of beams and columns. So that is shear deformation. So around 65% is due to bending of beams and only 15% is due to columns. Approximately around 80% of lateral drift that you can expect in this particular figure. And again, if you just look at the forces, so that is forces here, the bending moment and shear force, and deformations, so that is due to the external forces. Okay, when it is subjected to external force, the behavior of the particular frame. So this is the rigid frame of 5-story, right? And you can see the lateral forces are acting. So because of lateral forces, you can see that the deformation of the particular building, and these are the for this lateral force, external forces. So you'll get the member forces. So the member forces are bending moment as well as shear force. So this will be the shear force. So the shear force will be something like this, and the bending moment will be something like this. So these are all the member forces, right? So usually while after analysis, you will get the bending moment as well as shear force. So here the point of counterpressure, I hope you know that. So where the bending moment will be 0. So in if it is a uniform kind of a external load, so then you can expect the point load or the point of counterflexure will be exactly at the mid of the span. Understood? So this is a typical the force and deformation for the rigid frame. Okay, so this is a typical one. So due to the lateral load acting. Okay. And coming to the behavior, so very important. So from the structural design point of view, tall buildings, so because they are unusual height, so as the name indicates, tall building, and it is greater sensitive to wind as well as earthquake. So for the tall buildings, so you need to design for either earthquake or wind. So usually for the lower floors, so only gravity load is gravity in Bangalore. If you are constructing for G+5, so G+4 or 5, so if you consider the only dead load and live load, so it is more than enough. So where in case of tall buildings, so where you will be having the higher height of the building, right, because it is so sensitive for the wind as well as earthquake, so where you need to design for these two lateral forces, right? So are induced as lateral loads than the lower rise building, right? So estimating those lateral loads, okay, finding that lateral loads or estimating that lateral loads are play a major role in the design of tall structures. Okay, so that means so the lateral loads are due to the wind as well as earthquake. So the estimation of these loads are the plays a major role in the design of the tall buildings. So in order to find the effect of these lateral forces, so the design of tall buildings is very crucial. Okay, so and again it is more difficult in considering the lateral loads. So sorry, gravity loads. Gravity loads are vertical loads, right? So you can consider dead load and live load. And you can easily design the structural members. So where in case of tall buildings, so where it is considered for lateral loads, the designing each member, it is quite difficult when compared to the gravity load design. Okay, and again earthquake loads increases according to the building weight, wind load increases according to the building height. So as you know that let me so you know that already these things we have done in the numericals. So assume that this is the building. So when it is subjected to the wind load, so each floor, assume that these are the different floors. At each floor, the lateral loads are different, right? So at the higher floor, you'll be having maximum lateral load, at the lower floor you'll be having lesser wind load, right? Sorry, lesser lateral loads. So that particular thing that you can see over here. So earthquake loads increases according to the weight of the building. So in the typical floor, say because the base shear equals to what? So AH times of seismic weight. Okay. So if you are considering seismic weight of this particular floor is higher than this, so then this will be having the maximum lateral load. This will be having maximum lateral load when compared to others. So whichever is having the higher seismic load or seismic weight, okay, of that particular typical floor will be having maximum lateral load. So where in case of wind load increases according to the building height. So as you know that K2 is the factor, topography, terrain factor that we considered, right? Terrain factor or terrain category that we have considered. So that will be considered in order to find the wind pressure, that is Bz equals to K1 plus K2, K1 times of K2, K3 times of Vb. So Vb is the basic wind speed. So where K2 is varying, so this K2 value at the lower height, it is very small, when compared to the higher stories. Okay, so at the higher stories, this K2 value will be more, and at the lower level or lower height, this K2 value will be very less. So this K2 will influences the lateral load. So as height increases, this K2 value increases. That means if K2 is increasing, and these factors will be constant for all the height. Okay, this K1, K3, K4, and this design wind speed remains same for entire height of the building. But K2 is varying. So K2 is varying, and K2 is having maximum at the maximum height, right? So because of this K2 is varying, and you can see that, so the difference in the lateral load. Exactly at the higher floors will be having maximum the lateral load, that is due to wind load. So where in case of earthquake, so because of seismic weight, so you can see the difference in the lateral loads. If we are having a higher seismic weight, so then you'll be having the more lateral load. Okay, so that particular thing that you can see over here. So for this reason, the wind loads they are generally an important issue in the design of the structural system for low and mid buildings. Okay, so where in case of wind loads are not important in case of mid as well as low rise buildings. Okay, but it is play a sensitive role in the decisive, so that is very sensitive where in case of tall buildings. So when you are designing for tall buildings, so you must have to consider the wind loads. Okay, so even you can see this particular load, you can see this particular sentence can even be a cause of a large lateral drift sway that is more critical than earthquake loads. Okay, so that means, so in case of tall buildings, so the worst is earthquake, but while designing the tall building, so you have to consider the lateral load due to wind load because of large lateral drift. Okay, because of large lateral drift. So they are telling that, so for the tall buildings, it is wind load are more important when compared to the earthquake loads. Okay. So this is the difference in this. You can see what it is mentioned in this figure. So the kind of support, okay, this kind of support. So over here it is fixed support. So where you cannot see that there is a bending in this particular structural member. So where you have a hinge over here, where you have a hinge over here, you can see the buckling of the column, okay, due to the application of loads. Understood? So that difference that you can see, okay, here only the hinged frame and rigid frame. So in order to showcase the difference between the hinged frame and rigid frame, it is shown over here, okay. So where in case of fixed, this will be stable and there will be no buckling of the structural member, okay. And here this angle will be varying. So you can see this also. This angle will be varying because this will not bend. So this will remains as straight, and due to the continuous application of load, so this bending will getting change, okay. So this bending will getting change as this bending occurs after the completion of load. After the continuously applied load, so this theta will be varying, okay. So that depends on the load acting on this beam. So where it is acting, so where this particular angle will be maintained as 90, because this is again bending, again this is also bending, okay. So you can see that an uniform kind of the angle over here, so that is maintained as 90, and again this will be the deflection, right. So here only showcasing the difference between the hinge frame and rigid frame. So where in case of hinge frame, so the angle between the two member it is maintained uniformly, where it will be varying. Understood? Where in this case the columns also bending, okay, because of hinge support. So this is a kind of say for example, usually the beam and column are monolithically casted, right. So monolithically casted beams and columns are monolithically casted. So if say for example, if I cast columns initially, say then after that if I just install a kind of beam over here, so due to the application of lateral load, so what will happen, you can see the sway, right. So it is more, right. So the displacements are more because it is not monolithically casted. It is not monolithically casted. Here just placed the beams are placed above the columns. So this is not the usual procedure of the construction. So the usual procedure is the beams and columns are monolithically casted, okay, monolithically. So we are not going to cast as a separate. So we are not going to design, or you are not going to show the detailing the detailing over here will be the detailing of the column will be again passing on the beam, right. So the reinforcement will be passing on the beam, right. Again the beam the bending rod will be again, it will be placing on the columns. So where you can see the attachment, and you can expect a joint between beam and column, right. So this is not monolithically casted. So this is the columns are separately casted and beams are placed on that column. So then if I apply the lateral load, so where you can see the displacement over here, right. So you can see that the overturning of the base, right, rotations that you can see. So if I cast monolithically, so then if I apply the lateral load, so then you can see that the behavior of this particular structure. Okay, again here it is in support. So even in support, so this angle is maintained uniformly, right. So this angle is maintained uniformly, approximately 90, and you can see the moment over here, right? Moment over here because of rigid joint. So here there is no moment because of hinge support. So you can expect the rotation will be occur, right? So this is the typical bending moment diagram for hinge frame and rigid frame. So for rigid frame, it will be something like this. Okay, in hinge frame, so here you will be having the hinge support where you can see the rotation over here, the rotation over here. You cannot expect the bending moment over here, right? So you cannot expect any bending moment over here. So where it is fixed over here and it is fixed over here, so you can expect the bending moment in all the three sections. Okay, this is the typical bending moment diagram for hinge frame as well as the rigid frame. So you can see the differences, right? So in hinge frame, if I provide hinge frame, if I provide rigid frame, so what will be the structure? So more drift, where in case of hinge frame, increases axial load on the column. So because there is no bending moment, only axial load will be there, only axial load. So for the design of columns, the axial loads are predominant. So where you can expect a large axial load. So because of large axial load, so you may require the higher size of the members. Okay, you may require to go for higher size of column. So that you can see that. So large cross section of column. So cross section is nothing but size only, right? And increases the buckling in the column. So because of hinge support, you can expect the buckling in the column, right? So that we have seen in the previous figure, right? You can see the buckling of the column because of hinge support. So these are all the disadvantages where in case of hinge frame. So coming to the fixed one, decreases the axial load because bending moment will be there, right? So the joints are rigid. So because of a smaller axial load, so you can expect the smaller section in the smaller section of the column, and increases the buckling at the column. So that means it will restrict the resist the buckling of the column, right? And small deflection at beams. So because of rigid joint over here as well as over here, right? So due to the application of load, so you can see the transfer of loads are in a very good manner. So where you can, and you again it is fixed over here. So this can resist the maximum load. So because of this particular reason, where you can expect the smaller deflection. And again because of rigid joint, so it will gives very small deformations or displacements, right? Okay, so if you see the method of rigid frame design, so this is the typical floor plan with rigid frames. Okay, so this is the rigid frame, and these are the connections, rigid connections. So between the members, right? So rigid frames are used when architectural design will not allow a braced frame. Okay, so usually, so what will happen? Let me show you. So when you are going to prefer the rigid frame in case of tall buildings, so that is more important. So usually in the past also, in the present also, So usually for the tall structures, you'll be considering the braced frame structures in the tall buildings. Assume that you may, if I consider the braces, say this is the bracing. Assume this is one type of bracing. This is another type of bracing. Okay, I have just shown different types of bracings. So this is not in the building, you will not find these different types of bracing. Okay, only you can expect one or two types of kinds of braces. So if I just similarly, if I just draw the frame structure, rigid frame structure, it will be something like this. So there will be right. So between the frame, so you will not see any obstructions, right? So in case of this is rigid frame structure, this is braced frame structure. So when you are going to prefer the rigid frame and when you are going to prefer the braced frame, so usually for the construction of tall buildings, so will be followed, the first preference will keep the first preference as braced frames. Okay, so then when we need to consider these rigid frames, say for example in case of the architectural design and all, so where you need to provide doors over here, where you need to provide doors over here, where I need to provide the window over here. Okay, so those things are not possible in case of rigid frame structure. Okay, so the openings, the required kind of openings to required size, it may be door or ventilation or windows. Okay, so huge windows you need to provide, so that is not allowed in case of braced frames. Okay, because these bracings will be obstruction for these openings. Okay, so the required openings cannot be allowed in case of braced structure. So in that case, so you cannot compromise sometimes. So what they'll do, if you just go to the any site, so they'll compromise the safety, strength and all, but they'll not compromise in architectural views, right? So they are very rigid related to architectural views. So they sometimes they'll compromise in safety, strength and durability, but they'll not compromise related to architectural. So in that case, if openings are required, but it is not allowed in the braced frame structures, so then you need to prefer rigid frames. So where you'll be having the no obstruction between the frames, right? So between the frames, so you can see that there is no obstruction. So then you can easily provide the kind of opening. Okay, so required dimension or required kind of opening, right? So it is for that reason, so you can pick the rigid frame structural system. Okay, so that is what it is mentioned over here. So rigid frames are used when architectural designs will not allow the braced frames. So as I mentioned previously, I have shown with the figure. So where in case of braced structures, so you cannot accomplish with the architectural design. Okay, so in that case, so you are going to select or you are going to adopt the rigid frame structure. So this type of lateral resisting system generally do not have initial cost saving as a braced frame, but they have been better suited for the specific types of buildings. So what will happen in case of braced frames? So you can see in case of braced frames, there you can see the sections are very small. Okay, so the sections are very small, means the size of the structural components are very small when compared to the sizes of the structural components where in case of rigid frames. Okay, so that is one reason. And these are all the typical connections. And what are the advantages of rigid frame? So moments are redistributed. So this we have learned and we have designed while doing the continuous beam. So where you'll be having maximum, say assume that this is a continuous beam. Okay. So where you'll be having maximum the moments at the support, maximum moment at this support area. So and we have a very less moment in this particular region at the midpoint. So where you are going to transfer some amount of support moment to the moment at the midspan, right? So that is possible in case of rigid frame. So that is possible in case of rigid frame. So moments are redistributed. So the deflections are very small when compared to other structural systems when it is due to the lateral loads, and effective column lengths are shorter. Effective column lengths are shorter. So that means the length of the column are usually restricted to 8 feet, 10 feet, 12 feet, right? Or 2.8 meter, 3 meter, 3.2 meter. Okay. So the effective column height are very shorter. So the main advantage here is of the structural system, they do not have any structural walls, vertically oriented diagonal bracings. So as I mentioned previously, so where in case of this, so you will not find any kind of obstructions for the opening, and you will not find any structural walls or say concrete walls in the structural system. So rigid frames provide architectural freedom. Okay, the same points whatever that I have discussed previously. So the same points they have discussed here also. Okay, the rigid frames have given flexibility for architectural freedom. So this is one. So where you can expect the kind of designs, architectural freedom design that you can do, opening at the required position or required space, required size of the opening can be provided only in rigid frame. So you have a huge area for architecture, where here it is totally restricted in case of other structural systems. So that you can see as the major advantage. So rigid frames are typically imposes the smaller forces. Because of rigid connections, you can see the transfer of moments of forces. Okay, it will be equally distributed on all the structural members, where you can see the smaller forces on the foundation than the other structural system, right? Why? Because one more thing is here, the sections are somewhat larger when compared to shear walls. So you can see the section is very small. Okay, so it is of the width of the wall. Okay, it is almost equals to width of the wall. So for this you require the higher foundation area for foundation. So the greater foundation dimensions are required because of the larger forces and restricted by the smaller element. So where you require the more danger in case of the design of foundations for this kind of structural elements. And again we have a disadvantages also. So here rigid frames are not specifically detailed for seismic resistance with no special detailing criteria. So the code will not give any guidelines So for the rigid frame designs for the higher seismic zones and all. Okay. And again here also the frames are not permitted as the seismic forces resisting systems in seismic. So as I mentioned, higher zone factors. So in that areas, so this particular structural system is not suitable. Okay. So as we know that, so here in the rigid frame structure, the main structural components are beams and columns. You can see that for the higher buildings, for the tall buildings, so you'll be having the huge sections at the lower floors. Okay, so lower floors. So because of that, so you can see that the the cost of the building will increases because of huge sections at the lower floors having required the more quantity of steel as well as concrete and labors also, right? So coming to the next structural system, so that is braced frame system. So braced frames is a structural system commonly used in structures subjected to. So as same as all the structural systems. Okay. So this point you can add for all the structural systems. So this point can be added for all the structural system. So all the main function of the structural system is to resist the lateral loads. So which are all the lateral loads? The lateral loads are due to wind load as well as the earthquake load, right? And braced frames are generally made up of structural steel, can work effectively in both tension as well as compression. So in beams and columns that forms the frame. So as you know that, right, the combination of beam and columns forms a frame carrying vertical load, right? So that is gravity load, and bracing system carries the lateral load. Okay. So where in case of rigid frame, what will happen? So the gravity load has to be carried by the beam and column. The beam, right? It will be carried by it will be acting on beam and it will be carried by columns. Again, the seismic loads will be acting on the frame, right? Again, it will be carried by the same structural member. Where in case of the braced frames, where bracings are provided, the lateral loads, the vertical loads can be carried by this particular structural system, the frame as well as the frame that is combination of beam as well as columns, where the lateral loads are carried by these particular bracings. Okay. So you can see that, so the beams of the purpose of beams and columns are to resist only the vertical loads. So because of that, you can expect the smaller section in the beam and column. So where in case of rigid frame system, this is rigid frame system, this is braced frame system. So where you can see that both vertical loads as well as the seismic loads, or you can say lateral loads, has to be restricted by the same structural members. So you require the higher section, you may require the higher section of column as well as beams. So that is the greatest advantage where in case of braced structural system. Okay. So this point is very important. Okay, in bracing system, the beam and columns that forms a frame, right, carries the vertical load. So that is nothing but the gravity load. Okay, so here the bracing systems carries the lateral loads and position of the bracings. Okay, so this is more important. The positioning of braces, however, can be problematic, right? as they interface the design of the facade. So that means the architectural plays a major role in the major abstraction for the uh, braced building, braced frame structures. Okay, so you cannot place the opening at the required place in case of braced frames. So that is the greatest disadvantage in the braced frames. And the position of opening, right? Yeah, the building adapting high-tech or the post modernist style or have responded to this expressing bracings as an internal and external design features. So this is related to this is the introduction related to braced frames. Okay, so all the structural system, the main purpose of the structural system is to resist the lateral loads. So that may be due to wind load or it may be due to earthquake load.